And so today I want to talk about, well, there it is. It's up there. And before I do, I want, how many of you know this name, Matérn? Raise your hand if you just know the name Matérn in the context of geoscience. Not one. So I have to tell you, Simon was correct. Because he said, take that word out of your title. Nobody knows who that is. And you're not going to talk. Okay? And so for Simon, I chose this title. But I don't like this title because, and I want to emphasize this, that what I'm going to talk about today is more general than just this one application, which I will show you at the end. Okay? And by the way, if you go ask the people in your companies who work in the context of geostatistics, and then let me know if they don't know who Matérn is, right? But that name is quite well known in the context of spatial statistics, and of course geostatistics is that. All right, so just to give you an idea of why I'm focusing on the model covariance, here are some scattered measurements of porosity, and here's a model, right, which is porosity everywhere, that is consistent with those scattered measurements. Meaning if you go to the places where you had measurements, you would see exactly the same values here. Here's another model, also consistent. The only difference between these two models is the model covariance that was used in predicting the values where we did not have measurements. Okay, so that's really what I'm going to talk about today. And to do that effectively, I'm just going to briefly review least squares inverse theory. I know you've all seen this before, so this will just help you feel good about the notation, and again, that I hope you've seen as well. All right, so with geophysics, we can connect models to data. I don't think about necessarily the porosities I'm just talking about, think more generally. But let's assume that the data in this case are approximately equal to some linear function of the model, right? So that the geophysics in this case is, or could be, represented as a matrix multiplication, but it's just some linear operation between our data and model. And if it was nonlinear, we all know how to iterate around that nonlinearity. Okay, so let's just keep it simple and say it's linear. We also would likely have some notion of what the model should be. For example, porosities, we might say, on average, in this location might be 25%. Right? And that would be some useful information. So we would say that the true model needs to be somewhere around 25%, but could be higher or lower. All right? So the idea then in least squares inverse theory is to choose a model, find a model M, that minimizes the sum of these two terms. Right? The difference between the data and the geophysics, or what geophysics tells us the data should be, and then there's also that difference between the model and our a priori notion of what that model is. And there's a problem you recognize right away with this expression is that it's quite possible that the units of the data, and think seismic data for example, might have nothing to do with the units of the model. You can't simply add these terms. You want to make them dimensionless. And an easy way to do that would be to, okay, first I'll rewrite it, right? That's the same expression, but now written out, so that I can now put in the middle there a division by variances. Okay, so there's a data variance and a model variance. And the variance has the units of the data squared on the left, and then model squared on the right. So now we have dimensionless terms. And what do these variances mean? Right? So the data variance is some guess, maybe, or perhaps some better estimates of the uncertainty you have in your measurements. If you know you're likely to have errors in your measurements, then you would want to set sigma d to in a way that would reflect that uncertainty. It could also be that you know that there's something wrong with the geophysics, right? And there always is. Right? And so you might try to compensate for that somehow. That's a little bit trickier, but quite often we would just pick some reasonable measure of that uncertainty. In the model space, we're going to want to do more than just scale by some scalar number there. And so the more general form of this would be what you see here, where instead of a scalar division, we have an inverse of what's called the covariance matrix, right? So the covariance for the data, just keeping it general, and then also the model covariance. Okay? So the model covariance is CM. And the reason that it's a matrix is because it said, what this is saying, let's just focus on the model covariance. What it's saying is that in the inversion, it's okay if the model that we estimate is not the same as the a priori model. I mean, if it was the same, why did we bother to go collect data? Right? So it's going to be different. But what we're saying is that, the porosity, where I'm standing now, and the porosity a meter away, if I'm going to adjust this one, I probably should adjust this one too. And that's what the matrix does. If we didn't have a matrix there, then there'd be no constraint on how quickly or how rapidly our estimated model could vary. All right, so that was my quick review. And now let me show you, and I know you've seen this before, and you've probably done the calculus yourself, and you could do it in a minute, even if you hadn't, the least squares solution to that least squares problem. Give you a chance to kind of look at all the inverses that are in there, make sure you recognize it. Now, really, you could derive this pretty quickly. And I can remember a seminar where I was thinking about what I'm talking about today, and Paul Sava was there. And Paul came in, and essentially I wrote down, this is the answer. This is what you should be doing. Okay? And it was hard to argue. I could see it. It's pretty easy to derive. But I was using this one. Okay? Now I'll just put these side by side there. And so I can remember this really well because I said, okay, well, one of us got the derivation wrong, and Paul's was too easy to get. And so I went back and thinking, I must have gotten it wrong. Here, let me highlight the differences between those two solutions. Right, just so you can see them, right? Everything else is the same except the part that's highlighted there. Okay, well, do you know these are really the same solution? Yeah, you know this. Okay, so, and this, so it only, fortunately, it only took me, like 4 or 5 hours before I went to Tarantula's classic text on the theory of inverse problems, and I forget exactly what page it's on, but I think these two expressions are right next to one another. And I just forgotten it. And it's a marvelous matrix identity that says that those two things are equal. It's not hard to prove. When I look at it, though, I mean, we both looked at it and said, there's no way that these can both be right. And of course they are. All right. So that was just, ignorance on my part. But they are the same. Now that raises an interesting question. Which one should we use? Right? Because in theory they might be the same. But in practice, one might be a whole lot more efficient than the other. But one thing you might should think about, though, is that they really are only the same, and Tarantula says this, if all those inverses exist. Right? So think about the case where the measurement errors might be 0. That would mean that the matrix CD is 0, and you cannot use the top equation. Let's suppose the measurement errors are small. What that means is the top equation, the top solution, will lead to ill-conditioned systems that will require a lot of iterations to converge. And so don't say, well, we know that measurements errors are never 0. If they're small, you might still want to prefer the bottom solution. But another reason that most of us would probably choose the top solution is because of the fact that in the top solution you in effect are inverting a matrix that's in the model space, whereas in the bottom solution you're inverting a system in the data space. Now we never invert these systems, meaning we never actually form the matrices. I shouldn't say never. I've seen cases for 1D seismology or something like that where we might do that, but most of the time we cannot even store these matrices in memory. We're just going to need using iterative methods or something like that. And by the way, conjugate gradients works for both of these, because the matrices in parentheses are symmetric and positive definite. Right? But the reason most of us would probably use the matrix, the top solution, is because we have fewer model parameters than we have data. And so that makes fewer equations that we have to solve if we use the top equation. So think about seismic data, the number of samples of seismic data we have versus the number of model parameters. We typically have a lot more data than model. In the problem that I showed you earlier, remember that the data were in effect a subset of the model. So it was just the other way around. And then the bottom solution might be more appropriate. I'm going to show you an example of using the bottom solution a little bit later. But what I want to focus on mostly is this model covariance. Because no matter which of these solutions you use, you can still use this Matérn model covariance that I'm going to talk about here today. All right, so just a reminder that we're never actually going to build that matrix CM. I'm not going to tell you what the elements of those matrices are. Instead, I want to give you a recipe for multiplying by that matrix. Because if you multiply an image of random numbers, so this is a vector P, but you remember when I say a vector, it's really going to be an image. In the model space, there's no spatial correlation in the model space vector P, but when we apply the model covariance matrix to it, we get something which does have obvious spatial correlation. And that spatial correlation, you'll notice, is both anisotropic and spatially varying. Right? And I'll get going to that in just a moment. All right, so the first part I want to talk about is the model covariance, and then I'll show you that application that I mentioned earlier called tensor-guided Kriging. So first thing we need is a covariance function. And in geostatistics, these things are just everywhere. This is a common one because it's very simple. It's a decaying exponential, which says that the correlation between two samples of porosity decreases with the distance between those two samples. So samples are close together are more likely to have the same porosity than samples farther apart. That's just common sense. And the distance in this case has been normalized. In practice, you would divide R by some range, right? So that's a parameter that geostatisticians like to use, the range of the covariance function. And in this case, you can think of as the range as just 1, right? Because the exponent would have to have no units there. All right. Right. So this exponential covariance happens to be just one member of the Matérn family of covariance functions, which is described by the expression up above. And the family is parameterized by what's called the shape. So I mentioned the range parameter. The new parameter now is this thing called the shape. And I'm showing you just 4 different values there. 0.5 corresponds to the exponential covariance function that I showed you before. If we let nu go to infinity, that would be the Gaussian covariance function, which, by the way, most people don't want to use. It turns out it decays too quickly to 0. And so it's rarely used. And that's actually handy because, nu equals infinity would be hard to do, right? So more commonly, the parameter nu is chosen to be in the range I show here, between 0.5 and 1.5. And you'll notice that as we increase that parameter, the range, the extent of correlation is increasing as well. Right? So when you're changing one thing, the shape, you don't really want the range to change. And so in practice, what most people do is they scale distance by something like the square root of that shape parameter. So now all 4 of those covariance functions out of this Matérn family have more or less the same range. And what you can better see now is the effect of that parameter on the shape, especially for small distances. All right. This is a messy function. And probably the biggest reason people don't use this entire family, they might use the exponential, but this entire family requires a modified Bessel function of the second kind, a gamma function, and those are just, well, what did Rule say earlier today? Nobody learns about those things anymore anyway, right? So now you have some software, hopefully, that can compute these, but let's face it, exponential functions are a lot simpler. If you take the Fourier transform of this function, though, you get rid of that Bessel function. And this is true for any number of dimensions. Right? So R is like just distance, right? Euclidean distance here. And K here is the magnitude of wave number. So the Fourier transform is going to be symmetric around the origin wave number domain. We still have the gamma function, though, but we can get rid of that if we just let the number of dimensions be 2. Right? So now it's actually a pretty simple function, right? Regardless of the shape. And look at this function of wave number here. Notice that no matter what you choose for wave number, you get a positive number. It will never be 0, right? And it will also be symmetric. And this is just saying that your covariance function should be symmetric and positive definite. If you use this function, you will be guaranteed that the covariance matrix CM that I told you about before will also be symmetric and positive definite. And that's a strict requirement. All right, so how would you actually use this function to implement the covariance operator, right, or that model covariance? Here are two possibilities. In the top right, you see an integral, which is just convolution. So you can convolve with that function that I showed you before, and it'll be radially symmetric in 2 dimensions. And that'll get you from a vector or an image P to a vector Q, like what I showed you before. Alternatively, and in fact a lot more easily, right, you would just use an FFT. Just Fourier transform the vector in model space, that image, multiply by the expression that you see on the left, and then you would have the Fourier transform of the vector Q. Then inverse Fourier transform. Right? So that would be really easy. The problem with that, though, is that there's no way, if you do it with Fourier transforms, or even with the expression at the top, it's not obvious how you do it, to let this covariance be anisotropic and spatially varying. Right? And the spatially varying part is the real difficulty here. And that's why we can't simply use FFTs. And so instead of that Fourier transform on the right, let's use a differential equation. Now you know this is true because you remember that the Fourier transform of the Laplacian, and that's what's there, right? We just have the negative of the divergence of the gradient. So that's the negative of the Laplacian. The Fourier transform of that is wave number squared. Right? And to make this make sense, I just move the denominator onto the left-hand side. And so this is, I think of the Fourier transform on the left as a convenient shorthand for the differential equation on the right. Right? Now, don't talk this way to the geostatisticians, but I can tell you this, right, for people in this room, you can think of the top right equation as the Kirchhoff solution, right? And then the bottom right equation would be the finite difference solution. Right? And one of the things we like about finite difference equations, right, is that it's easy to let the parameters in that differential equation vary spatially. And that was hard to do with the Fourier transform. Now this covariance function that this differential equation that you see here was proposed before I was born, by Whittle. And it's just kind of amazing to me that people in spatial statistics were proposing these kinds of model covariances, and Whittle was working in the context of forestry, and he was analyzing the spatial statistics of orange trees. Right? Nothing to do with geostatistics, but he actually, in this paper, 1954, wrote down this equation. And Matérn had done something even more general about the same time. They were working independently. Some people today actually call this the Whittle-Matérn covariance, but I'll do what most people do and just call it the Matérn covariance. So in this paper, you have to think about this is before digital computers, were widely available. And maybe he was using an analog computer. I don't know how he actually did this, but he actually was using this equation, and he was troubled by the fact that what does this equation mean if nu is not an integer? Right? Does that bother you too? Right? A little bit. Like how are you actually going to solve this differential equation if nu has the value 0.5? That's the exponential covariance. And for this reason, Whittle argued that for 2 dimensions, it would be different for 1D or 3D, but in 2 dimensions, the most natural choice of that shape parameter, just based on physics, I guess, or something, he was reasoning about that somehow his orange trees were governed by a differential equation, and if that was true, then nu had to be 1, right? Because then you would just have a differential operator multiplied by a differential operator, the same thing, And you could implement that. You could solve that differential equation. But how are you going to solve this equation? And what does it even mean if nu is not an integer? Okay, so that's one problem. The other problem is, after all of this, I still haven't shown you how we're going to make this implementation of model covariance anisotropic and spatially varying. Actually, I gave you a hint before, and here's just the answer. Right? So D here is in 2 dimensions, a 2 by 2 matrix. It's a tensor. It's symmetric and positive definite. It describes the anisotropy, and because D can vary with location, right? That's what makes now this model covariance both anisotropic and spatially varying. All right, so if you solve this differential equation, right, with P on the right-hand side known, and you solve for Q, you have in effect applied the model covariance to P and gotten Q. Right? Except, now wait a minute, what are you going to do if nu is not an integer? So in the report, I actually have a table of parameters that will let this sequence of equations approximate the one I just showed you before. All right, so I'll highlight the 3 parameters that go into that approximation. So you give me a nu, and here, just for simplicity, I'm going to say nu is between 0 and 1. Okay, that's not required, but it just gets a little more complicated. You have to add an extra equation if nu is between 1 and 2. Right, so you tell me the parameter of nu, and then in the report, I just give you a table that will tell you how to choose the parameters alpha, beta, and gamma. And I chose those 3 fitting parameters to match the Matérn covariance. It's not the Matérn covariance. It's actually what I'll call a smoothing covariance, because the middle 2 equations that you see here are those so-called local smoothing filters. When Ziming was talking about using those filters to compute structure tensors, right, he was solving those differential equations. So what I liked about this is I already had software that's as fast as I know how to make it to solve the 2 middle equations. And that's the hard part. Right, so let me show you what the Matérn covariance is again, and show you what the approximation is. Right? Because it is an approximation. This is not exactly, well, you see it there. It's, the approximation symbol is correct. Okay, so this is Matérn, and this is what I call this smoothing covariance. Smoothing covariance is almost a tautology, because it's, any model covariance that you use is going to in some way smooth. But this is the smoothing I'm talking about here is this one that involves solving those 2 differential equations. Here is the range-adjusted covariance, Matérn covariance, and here's the range-adjusted smoothing covariance. So they're not the same, but in practice they're probably good enough to give you this shape parameter where you can tune your model covariance in the same way geostatisticians in your companies might also be tuning these parameters for modeling reservoirs. All right, so here are these 4 equations again, and let me show you how to use these just to compute this new image Q if you were given an image P. Right, so I'm going to show you how to go this way. Right, to in effect multiply by the model covariance. So the first thing you do is you solve for Q naught. This is actually really easy. The term you see in vertical brackets, that's just the determinant of D. And so this is a sample by sample scaling of P. So once you have Q naught, you have the right-hand side for the second differential equation. Solve it for Q1. Once you know Q1, you can solve for Q2. And finally, given Q2, you can get what we wanted in the first place. Now you could actually do all this at once, but it would be slower. It's actually faster to solve 2 second-order differential equations than to solve 1 fourth-order differential equation. All right, now you can go, if you go this way, you compute the images I've already shown you. Right? This is in effect multiplying by the model covariance without ever constructing that model covariance matrix. You can also go the other way. Right? So we could go from the smooth model to the rough one, but what I'm showing you here is how to implement the inverse of this smoothing covariance. Because you might want to be using the top equation that I have, the other solution to the least squares problem, right? The one where you want it to work in the model space. And this is how you would do it. Or more specifically, this is what you would do. You would start with Q, and then you would solve the bottom equation for Q2. With given Q2, you apply a differential operator. You don't even have to solve differential equations now. You just compute derivatives to get Q1. Same goes to get Q0. And at the very end, again, these are not differential equations, the top and the bottom ones here. Easy to solve. Okay? So then you can go the other way. The last thing I haven't told you, I'll leave this up here for a minute, I haven't told you is how you come up with these tensors D, but I think you've seen examples of that, and you're going to see more of them here from ASON. I'm going to get them here from a seismic image. So this is a horizon slice. It's not a constant depth or constant time slice. It's a slice of seismic amplitude along a horizon. So there's no structure here. The changes in amplitude you see here are almost entirely due to stratigraphy, which is pretty obvious, the channel features you see there. And from an image of that sort, we can compute this tensor field D, which is a 2x2 matrix at every location, and here I'm just showing you a subset. And so the ellipses are elongated in directions in which the correlation is highest. And so we're using the seismic image to infer a model of spatial correlation that we're going to use in a linear inverse problem for something else entirely. In this case, porosity. Okay, so this leads to the application I'm going to show you. But just remember this, before I get into the application of Kriging, understand that you can use everything I've shown you in any inverse problem where you need a model covariance matrix. And you may be thinking I use regularization instead, but that's what Tarantola showed us, is that, and others before him, I suppose, but he made it really clear to me, reading his text, of this is what you should be doing. But by the way, this is match filtering too, right? It's really it's the same stuff, but in the most general form of match filtering are those equations from Tarantola's text. All right, so in the Kriging problem, we have a subset of our model. Those are the measurements, places where we've measured porosity, and our goal is to predict, right, this is spatial prediction of the porosities where we don't have measurements. And so here again are those two solutions, and because our data space is a subset, our data are just a subset of the model, and because I'm going to let CD go to 0, I'm going to choose the bottom equation. And this is simple Kriging. And the word Kriging, I think, never appears in Tarantola's text. Right? But it does appear in some papers that he wrote later with geostatisticians at Stanford, where he spent some time. And so I think you'll enjoy reading those papers to see other applications of a good model covariance. All right, so I'm going to use this one, and I'm going to let CD go to 0, which I can do, right? There's no problem there. We don't have the inverse of CD. And then I'm going to solve for this model, this least squares solution, and tilde, using conjugate gradients, right? Because once you have a way of applying the matrix in parentheses there, you have a way of solving this system of equations with a conjugate gradient solver. All right, so here are the scattered data, and then here are the results of doing that tensor-guided Kriging that I showed you before. Okay, just solving least squares problem, but using that model covariance, as I showed before. In this case, the parameter nu is equal to 1, as Whittle suggested it should be. Just for comparison, let me show you the result you would get if you just assumed isotropic and spatially invariant model covariance. Oh, I'm sorry. This is the true model. I should show you that first. Why do I know the true models? Because all the data were synthetic here. Right? So I constructed this model, which is clearly, the statistics of this are in no way isotropic or constant. The orientation of the anisotropy is changing in space. And if you ignored that, if you just said that the correlation is isotropic and constant, so stationary, this is what we get, right? So this is Kriging with an isotropic and spatially invariant model covariance. And if you just use Kriging from a MATLAB package, or for most software with Kriging, there will be a default model covariance. And chances are it's going to be isotropic and stationary. You might be able to specify anisotropy, but I don't think I've ever seen any Kriging software allow you to specify a anisotropic and spatially varying covariance. I've not seen it. If you've seen it, I'd like to know about it so I know where to look. Right, so I think this is a new result, to be able to do Kriging with such a model covariance. And as Tariq said, he showed pictures, I mean, this is the Earth. Right? There's just no reason to believe that spatial correlation to the subsurface should be isotropic and certainly not stationary. Okay, let me show you one more result, because ASON in a moment is going to show you even more of these. And this is a process which I talked about 4 or 5 years ago called blended neighbor interpolation. It has nothing to do with least squares inverse theory. Not at all. It's actually an extension of a classic method for interpolation called natural neighbor or Simpson interpolation. And the extension is to enable it to use that tensor field D as a anisotropic and spatially varying correlation model. But it's not the same as a model covariance. It's nothing to do with least squares inverse theory, but it's actually pretty close to what you get with the Kriging solution. I mean, a lot better than just assuming isotropy. Right? So I'll just flip back and forth. All right, so similar, but with this blended neighbor interpolation, there's no really easy way to put in the measurement errors. It's trivial to put in some data covariance, right, into the Kriging, the simple Kriging solution. It's hard to do here. I mean, it doesn't even work right? You're doing everything kind of ad hoc. Farhad knows about this. He talked about an example of doing this before. All right, so here again is the true model for comparison. And I just want to end by reminding you that in my case, I've used the seismic image to derive a model covariance that was then used to solve that inverse problem, to predict porosities where they were not measured. I have not used seismic amplitude directly by saying that seismic amplitude should itself be correlated with porosity. That's a different assumption. In fact, it wouldn't even be valid, but you might be thinking, well, what about seismic impedance? Because often seismic impedance does exhibit a high correlation with porosity, and we use that. And when we do that, we're doing something different entirely. That's co-Kriging. This is different. I'm just using the seismic amplitudes here to derive this model of spatial correlation. And I'll again remind you that Kriging is just one application. You can use this to derive image-guided inversions of many sorts, and including the work that Jay and Andre Reveal are doing at Mainz. Thank you.